Chapter 1. Newton. In speaking of Newton, we are tempted to paraphrase a line from the scriptures. Before Newton, the solar system was without form and void. Then Newton came, and there was light. To have discovered a law, not only applicable to matter on this earth, but to the planets and sun and stars beyond, is a triumph which places Newton among the supermen. What Newton's law of gravitation must have meant to the people of his day can be pictured only if we conceive what the effect upon us would be if someone, say Marconi, were actually to succeed in getting into touch with beings on another planet. Newton's law increased confidence in the universality of earthly laws, and it strengthened belief in the cosmos as a law-abiding mechanism. The attraction between any two bodies is proportional to their masses and inversely proportional to the square of the distance that separates them. This is the concentrated form of Newton's law. If we apply this law to such bodies as the sun and the earth, we can state that the sun attracts the earth and the earth the sun. Furthermore, this attractive power will depend upon the distance between these two bodies. Newton showed that if the distance between the sun and the earth were double, the attractive power would be reduced not to 1/2, but to 1/4. If treble, the attractive power would be reduced to 1/9. If, on the other hand, the distance were halved, the attractive power would be not merely twice, but 4 times as great. And what is true of the sun and the earth is true of every body in the firmament. And, as Professor Rutherford has recently shown, even of the bodies which make up the solar system of the almost infinitesimal atom, this mysterious attractive power that one body possesses for another is called gravitation, and the law which regulates the motion of bodies when under the spell of gravitation is the law of gravitation. This law we owe to Newton's genius. We can best appreciate Newton's momentous contribution to astronomy by casting a rapid glance over the state of the science prior to the 17th century, that is, prior to Newton's day. Ptolemy's conception of the earth as the center of the universe held undisputed sway throughout the Middle Ages. In those days, Ptolemy was in astronomy what Aristotle was in all other knowledge. They were the gods who could not but be right. Did not Aristotle say that earth, air, fire, and water constituted the 4 elements? Did not Ptolemy say that the earth was the center round which the sun revolved? Why, then, question further? Questioning was a sacrilege. Copernicus, however, did question. He studied much and thought much. He devoted his whole life to the investigation of the movements of the heavenly bodies, and he came to the conclusion that Ptolemy and his followers in succeeding ages had expounded views which were diametrically opposed to the truth. The sun, said Copernicus, did not move at all, but the earth did, and far from the earth being the center of the universe, it was but one of several plans. The influence of the church, coupled with man's inclination to exalt his own importance, strongly tended against the acceptance of such heterodox views. Among the many hostile critics of the Copernican system Tycho Brahe stands out preeminently. This conscientious observer bitterly assailed Copernicus for his suggestion that the Earth moved, and developed a scheme of his own which postulated that the planets revolved around the Sun, and planets and Sun in turn revolved around the Earth. The majority applauded Tycho. A small, very small group of insurgents had faith in Copernicus. The illustrious Galileo belonged to the minority. The telescope of his invention unfolded a view of the universe which belied the assertions of the many and strengthened his belief in the Copernican theory. It explains to me the cause of many phenomena which under the generally accepted theory are quite unintelligible. I have collected arguments for refuting the latter, but I do not venture to bring them to publication. So wrote Galileo to his friend Kepler. I do not venture to bring them to publication. How significant of the times of any time, one ventures to add. Galileo did overcome his hesitancy and published his views. They roused a storm. Look through my telescope, he pleaded, but the professors would not, neither would the body of inquisitors. The Inquisition condemned him. The proposition that the Sun is in the center of the Earth and immovable from its place is absurd, philosophically false, and formally heretical, because it is expressly contrary to the Holy Scriptures, and poor Galileo was made to utter words, which were as far removed from his thoughts as his oppressors' ideas were from the truth. I abjure, curse, and detest the said errors and heresies. The truth will out. Others rose who defied the majority and the powerful Inquisition. Most prominent of all of these was Galileo's friend, Kepler. Though a student of Tycho, Kepler did not hesitate to espouse the Copernican system, but his adoption of it did not mean unqualified approval. Kepler's criticism was particularly directed against the Copernican theory that the planets revolve in circles. This was boldness in the extreme. Ever since Aristotle's discourse on the circle, as a perfect figure, it was taken for granted that motion in space was circular. Nature is perfect, the circle is perfect, hence, if the Sun revolves, it revolves in circles. So strongly were men imbued with this perfection, that Copernicus himself fell victim. The Sun no longer moved, but the Earth and the planets did, and they moved in a circle, radical as Copernicus was. A few atoms of conservatism remained with him still. Not so Kepler. Tycho had taught him the importance of careful observation to such good effect that Kepler came to the conclusion that the revolution of the Earth around the Sun takes the form of an ellipse rather than a circle, the Sun being stationed at one of the foci of the ellipse. To picture this ellipse, we shall ask the reader to stick the pens a short distance apart into a piece of cardboard, and to place over the pens a loop of string. With the point of a pencil, draw the loop taut as the pencil moves around the two pens the curve. So produced will be an ellipse. The positions of the two pens represent the two foci. Kepler's observation of the elliptical rotation of the planets was the first of three laws, quantitatively expressed, which paved the way for Newton's law. Why did the planets move in just this way? Kepler tried to answer this also, but failed. It remained for Newton to supply the answer to this question. The Great Plague of 1666 drove Newton from Cambridge to his home in Lincolnshire. There, according to the celebrated legend, the philosopher, sitting in his little garden one fine afternoon, fell into a deep reverie. This was interrupted by the fall of an apple, and the thinker turned his attention to the apple and its fall. It must not be supposed that Newton discovered gravity. Apples had been seen to fall before Newton's time, and the reason for their return to Earth was correctly attributed to this mysterious force of attraction possessed by the Earth, to which the name gravity had been given. Newton's great triumph consisted in showing that this gravity, which was supposed to be a peculiar property residing in the Earth, was a universal property of matter, that it applied to the moon and the sun as well as to the Earth, that, in fact, the motions of the moon and the planets could be explained on the basis of gravitation. But his supreme triumph was to give, in one sublime generalization, quantitative expression to the motion regulating heavenly bodies. Let us follow Newton in his train of thought. An apple fall from a tree 50 yards high, it would fall from a tree 500 yards high. It would fall from the highest mountain top several miles above sea level. It would probably fall from a height much above the mountain top. Why not? Probably the further up you go, the less does the Earth attract the apple. But at what distance does this attraction stop entirely? The nearest body in space to the Earth is the Moon, some 240,000 miles away. Would an apple reach the Earth thrown from the Moon? But perhaps the Moon itself has attractive power. If so, since the apple would be much nearer the Moon than the Earth, the probabilities are that the apple would never reach the Earth. But hold, the apple is not the only object that falls to the ground. What is true of the apple is true of all other bodies of all matter, large and small. Now there is the Moon itself, a very large body. Does the Earth exert any gravitational pull on the Moon? To be sure, the Moon is many thousands of miles away, but the Moon is a very large body, and perhaps this size is in some way related to the power of attraction. But then if the Earth attracts the Moon, why does not the Moon fall to the Earth? A glance at the accompanying figure will help to answer this question. We must remember that the Moon is not stationary, but traveling at tremendous speed, so much so that it circles the entire Earth every month. Now, if the Earth were opposite the path of the Moon, would be a straight line, say MB. If, however, the Earth exerts attraction, the Moon would be pulled inward. Instead of following the line MB, it would follow the curved path MB, and again, the Moon having arrived at B, is prevented from following the line BC, but rather BC, so that the path, instead of being a straight line, tends to become curved. From Kepler's researches, the probabilities were that this curve would assume the shape of an ellipse rather than a circle. The only reason, then, why the Moon does not fall to the Earth is on account of its motion. Were it to stop moving even for the fraction of a second, it would come straight down to us, and probably few would live to tell the tale. Newton reasoned that what keeps the Moon revolving around the Earth is the gravitational pull of the latter. The next important step was to discover the law regulating this motion. Here Kepler's observations of the movements of the planets around the Sun was of inestimable value, for from these Newton deduced the hypothesis that attraction varies inversely as the square of the distance. Making use of this hypothesis, Newton calculated what the attractive power possessed by the Earth must be in order that the Moon may continue in its path. He next compared this force with the force exerted by the Earth in pulling the apple to the ground and found the forces to be identical. I compared, he writes, the force necessary to keep the Moon in her orb with the force of gravity at the surface of the Earth and found them answer pretty nearly. One and the same force pulls the Moon and pulls the apple, the force of gravity. Further, the hypothesis that the force of gravity varies inversely as the square of the distance had now received experimental confirmation. The next step was perfectly clear. If the Moon's motion is controlled by the Earth's gravitational pull, why is it not possible that the Earth's motion, in turn, is controlled by the Sun's gravitational pull? That, in fact, not only the Earth's motion, but the motion of all the planets is regulated by the same means. Here again Kepler's pioneer work was a foundation comparable to reinforced concrete. Kepler, as we have seen, had shown that the Earth revolves around the Sun in the form of an ellipse, one of the foci of this ellipse being occupied by the Sun. Newton now proved that such an elliptic path was possible only if the intensity of the attractive force between Sun and planet varied inversely, as the square of the distance, the very same relationship that had been applied with such success in explaining the motion of the Moon around the Earth. Newton showed that the Moon, the Sun, the planets, every body in space conform to this law. The Earth attracts the Moon, but so does the Moon the Earth. If the Moon revolves around the Earth, rather than the Earth around the Moon, it is because the Earth is a much larger body, and hence its gravitational pull is stronger. The same is true of the relationship existing between the Earth and the Sun. When we speak of the Earth attracting the Moon, and the Moon the Earth, what we really mean is that every one of the myriad particles composing the Earth attracts every one of the myriad particles composing the Moon, and vice versa. If in dealing with the attractive forces existing between a planet and its satellite or a planet and the Sun, the power exerted by every one of these myriad particles would have to be considered separately, then the mathematical task of computing such forces might well appear hopeless. Newton was able to present the problem in a very simple form by pointing out that in a sphere such as the Earth or the Moon, the entire mass might be considered as residing in the center of the sphere. For purposes of computation, the Earth can be considered a particle with its entire mass concentrated at the center of the particle. This viewpoint enabled Newton to extend his law of inverse squares to the remotest bodies in the universe. If this great law of Newton's found such general application beyond our planet, it served an equally useful purpose in explaining a number of puzzling features on this planet. The ebb and flow of the tides was one of these puzzles. Even in ancient times it had been noticed that a full moon and a high tide went hand in hand, and various mysterious powers were attributed to the satellite and the ocean. Newton pointed out that the height of the water was a direct consequence of the attractive power of the moon, and to a lesser extent because further away of the sun. One of his first explanations, however, dealt with certain irregularities in the moon's motion around the Earth. If the solar system would consist of the Earth and moon alone, then the path of the moon would be that of an ellipse, with one of the foci of this ellipse occupied by the Earth. Unfortunately for the simplicity of the problem, there are other bodies relatively near in space, particularly that huge body, the Sun. The Sun not only exerts its pull on the Earth, but also on the Moon. However, as the Sun is much further away from the Moon than is the Earth's attraction for its satellite is much greater, despite the fact that the Sun is much huger and weighs far more than the Earth. The greater pull of the Earth in one direction, and the lesser pull of the Sun in another, places the poor Moon between the devil and the deep sea. The situation gives rise to a complexity of forces, the net result of which is that the Moon's orbit is not quite that of an ellipse. Newton was able to account for all the forces that come into play, and he proved that the actual path of the Moon was a direct consequence of the law of the inverse squares in actual operation. The law of gravitation, embodying also laws of motion, which we shall discuss presently, was first published in Newton's immortal Principia. A selection from the preface will disclose the contents of the book and, incidentally, the style of the author. We offer this work as mathematical principles of philosophy, for all the difficulty in philosophy seems to consist in this from the phenomena of motions, to investigate the forces of nature, and then from these forces to demonstrate the other phenomena, and to this end the general propositions in the first and second book are directed. In the third book we give an example of this, in the explication of the system of the world, for by the propositions mathematically demonstrated in the first book, we there derive from the celestial phenomena the forces of gravity with which bodies tend to the Sun and the several planets. Then, from these forces, by other propositions which are also mathematical, we deduce the motions of the planets, the comets, the moon, and the sea. I wish we could derive the rest of the phenomena of nature by the same kind of reasoning from mechanical principles, for I am induced by many reasons to suspect that they may all depend upon certain forces by which the particles of bodies, by some causes hitherto unknown, are either mutually impelled towards each other and cohere in regular figures, or are repelled and recede from each other. At this point we may state that neither Newton, nor any of Newton's successors, including Einstein, have been able to advance even a plausible theory as to the nature of this gravitational force. We know that this force pulls a stone to the ground, we know, thanks to Newton, the laws regulating the motions due to gravity. But what this force we call gravity really is, we do not know. The mystery is as deep as the mystery of the origin of life. Professor Einstein writes Professor Eddington as sought, and has not reached any ultimate explanation of its cause. A certain connection between the gravitational field and the measurement of space has been postulated, but this throws light rather on the nature of our measurements than on gravitation itself. The relativity theory is indifferent to hypotheses as to the nature of gravitation, just as it is indifferent to hypotheses as to the nature of light. In his Principia, Newton begins with a series of simple definitions dealing with matter and force, and these are followed by his three famous laws of motion: the nature and amount of the effort required to start a body moving, and the conditions required to keep a body in motion are included in these laws. The fundamentals, mass, time, and space, are exhibited in their various relationships. Of importance to us particularly is that in these laws, time and space are considered as definite entities, and as two distinct and widely separated manifestations. We shall see that in Einstein's hands a very close relationship between these two is brought about. Both Newton and Einstein were led to their theory of gravitation by profound studies of the mathematics of motion, but as Newton's conception of motion differed from Einstein's, and as, moreover, important discoveries into the nature of matter and the relationship of motion to matter were made, subsequent to Newton's time, we need not wonder that the two theories show divergence, that, as we shall see, Newton's is probably but an approximation of the truth. If we confine our attention to our own solar system, the deviation from Newton's law is, as a rule, so small as to be negligible. Newton's laws of motion are really axioms, like the axioms of Euclid. They do not admit of direct proof, but there is this difference, that the axioms of Euclid seem more obviously true. For example, when Euclid informs us that things which are equal to the same thing are equal to one another, we have no hesitation in accepting this statement, for it seems so self-evident. When, however, we are told by Newton that the alteration of motion is ever proportional to the motive force impressed, we are at first somewhat bewildered with the phraseology. And then, even when that has been mastered, the readiness with which we respond will probably depend upon the amount of scientific training we have received. Every body continues in its state of rest, or of uniform motion in a straight line, unless it is compelled to change that state by forces impressed thereon. So runs Newton's first law of motion. A body does not move unless something causes it to move. To make the body move, you must overcome the inertia of the body. On the other hand, if a body is moving, it tends to continue moving, as witness our forward movement when the train is brought to a standstill. It may be asked, why does not a bullet continue moving indefinitely once it has left the barrel of the gun? Because of the resistance of the air which it has to overcome, and the path of the bullet is not straight because gravity acts on it and tends to pull it downwards. We have no definite means of proving that a body once set in motion would continue moving for an indefinite time and along a straight line. What Newton meant was that a body would continue moving, provided no external force acted on it. But in actual practice, such a condition is unknown. Newton's first law defines force as that action necessary to change a state of rest or of uniform motion, and tells us that force alone changes the motion of a body. His second law deals with the relation of the force applied and the resulting change of motion of the body. That is, it shows us how force may be measured. The alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. Newton's third law runs: to every action there is always opposed an equal reaction. The very fact that you have to use force means that you have to overcome something of an opposite nature. The forward pull of a horse towing a boat equals the backward pull of the tow rope connecting boat and horse. Many people, says Professor Watson, find a difficulty in accepting this statement, since they think that if the force exerted by the horse on the rope were not a little greater than the backward force exerted by the rope on the horse, the boat would not progress. In this case, we must, however, remember that, as far as their relative positions are concerned, the horse and the boat are at rest, and form a single body, and the action and reaction between them, due to the tension on the rope, must be equal and opposite, for otherwise there would be relative motion, one with respect to the other. It may well be asked, what bearing have these laws of Newton on the question of time and space? Simply this, that to measure force the factors necessary are the masses of the bodies concerned, the time involved, and the space covered, and Newton's equations for measuring forces assume time and space to be quite independent of one another. As we shall see, this is in striking contrast to Einstein's view. In 1665, when but 23 years old, Newton invented the binomial theorem and the infinitesimal calculus, two phases of pure mathematics which have been the cause of many a sleepless night. To college freshmen, had Newton done nothing else, his fame would have been secure. But we have already glanced at his law of inverse squares and the law of gravitation. We now have to turn to some of Newton's contributions to optics, because here more than elsewhere we shall find the starting point to a series of researches which have culminated so brilliantly in the work of Einstein. Newton turned his attention to optics in 1666, when he proved that the light from the sun, which appears white to us, is in reality a mixture of all the colors of the rainbow. This he showed by placing a prism between the ray of light and a screen. A spectrum showing all the colors from red to violet appeared on the screen. Another notable achievement of his was the design of a telescope which brought objects to a sharp focus and prevented the blurring effects which had occasioned so much annoyance to Newton and his predecessors in all their astronomical observations. These and other discoveries of very great interest were brought together in a volume on optics which Newton published in 1704, Our particular concern here is to examine the views advanced by him as to the nature of light. That the nature of light should have been a subject for speculation even to the ancients need not surprise us if other senses, as touch, for example, convey impressions of objects. It is true to say that the sense of sight conveys the most complete impression. Our conception of the external world is largely based upon the sense of sight, particularly so when we deal with objects beyond our reach in astronomy. Therefore, a study of the properties of light is indispensable. But what is this light? We open our eyes and we see. We close our eyes and we fail to see. At night in a dark room we may have our eyes open, and yet we do not see. Then light must be absent. Evidently, light does not wholly depend upon whether our eyes are open or closed. This much is certain: the eye functions, and something else functions. What is this something else? Strangely enough, Plato and Aristotle regarded light as a property of the eye and the eye alone. Out of the eye tentacles were shot which intercepted the object, and so illuminated it. From what has already been said, such a view seems highly unlikely. Far more consistent with their philosophy in other directions would have been the theory that light has its source in the object and not in the eye, and travels from object to eye rather than the reverse. How little substance the Aristotelian contribution possesses is immediately seen when we refer to the art of photography. Here light rays produce effects which are independent of any property of the eye. The blind man may click the camera and produce the impression on the plate. Newton, of course, could have fallen into no such error as did Plato and Aristotle. The source of light to him was the luminous body. Such a body had the power of emitting minute particles at great speed, and these, when coming in contact with the retina, produce the sensation of sight. This emission, or corpuscular theory of Newton's, was combated very strongly by his illustrious Dutch contemporary, Huygens, who maintained that light was a wave phenomenon, the disturbance starting at the luminous body and 23 spreading out in all directions. The wave motions of the sea offer a certain analogy. Newton's strongest objection to Huygens' wave theory was that it seemed to offer no satisfactory explanation as to why light traveled in straight lines. He says, "To me the fundamental supposition itself seems impossible, namely that the waves or vibrations of any fluid can, like the rays of light, be propagated in straight lines without a continual and very extravagant bending and spreading every way into the quiescent medium, where they are terminated by it. I mistake if there be not both experiment and demonstration to the contrary." In the corpuscular theory, the particles emitted by the luminous body were supposed to travel in straight lines. In empty space, the particles traveled in straight lines and spread in all directions. To explain how light could traverse some types of matter liquids, for example, Newton supposed that these light particles traveled in the spaces between the molecules of the liquid. Newton's objection to the wave theory was not answered very convincingly by Huygens. Today we know that light waves of high frequency tend to travel in straight lines, but may be prevented 24 from doing so by gravitational forces of bodies near its path. But this is Einstein's discovery. A very famous experiment by Foucault in 1853 proved beyond the shadow of a doubt that Newton's corpuscular theory was untenable. According to Newton's theory, the velocity of light must be greater in a denser medium such as water than in a lighter one such as air. According to the wave theory, the reverse is true. Foucault showed that light does travel more slowly in water than in air. The facts were against Newton and in favor of Huygens, and where facts and theory clash there is but one thing to do: discard the theory. Newton was a Cambridge man, and Newton made Cambridge famous as a mathematical center. Since Newton's day, Cambridge has boasted of a clerk Maxwell and a Rayla, and her Larmor, her J.J. Thomson, and her Rutherford are still with us. Newton entered Trinity College when he was 18, and soon threw himself into higher mathematics in 1669, when but 27 years old. He became professor of mathematics at Cambridge, and later represented that seat of learning in Parliament. When his friend Montague became Chancellor of the Exchequer, Newton was offered and accepted the lucrative position of Master of the Mint. As President of the Royal Society, Newton was occasionally brought in contact with Queen Anne. She held Newton in high esteem, and in 1705 she conferred the honor of knighthood on him. He died in 1727. I don't know, wrote Newton, what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and directing myself in now, and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. Such was the modesty of one whom many regard as the greatest intellect of all ages. Chapter 2: The Ether and Its Consequences. Huygens' wave theory of light, now so generally accepted, loses its entire significance if a medium for the propagation of these waves is left out of consideration. This medium we call the ether. Huygens' reasoning may be illustrated in some such way as this: if a body moves, a force pushes or pulls it. That force itself is exemplified in some kind of matter, say a horse. The horse in pulling a cart is attached to the cart. The horse in pulling a boat may not be attached to the boat directly, but to a rope, which in turn is attached to the boat. In common cases where one piece of matter affects another, there is some direct contact, some go-between. But cases are known where matter affects matter, without affording us any evidence of contact. Take the case of a magnet's attraction for a piece of iron. Where is the rope that pulls the iron towards the magnet? Perhaps you think the attraction due to the air in between the magnet and iron, but removing the air does not stop the attraction. Yet how can we conceive of the iron being drawn to the magnet? unless there is some go-between, some medium not readily perceptible to the senses perhaps, and therefore not strictly a form of matter. If we can but picture some such medium, we can imagine our magnet giving rise to vibrations in this medium which are carried to the iron. The magnet may give rise to a disturbance in that portion of the medium nearest to it. Then this portion hands over the disturbance to its neighbor, the next portion of the medium, and so on, until the disturbance reaches the iron. You see, we are satisfying our sense perception by arguing in favor of action by actual contact rather than some vague action at a distance. The go-between, instead of being a rope, is the medium called the ether. Foucault's experiment completely shattered the corpuscular theory of light, and for want of any other more plausible alternative, we are thrown back on Huygens' wave theory. It will presently appear that this wave theory has elements in it which make it an excellent alternative. In the meantime, if light is to be considered as a wave motion, then the query immediately rises: what 29 is the medium through which these waves are propagated? If water is the medium for the waves of the sea, what is the medium for the waves of light? Again we answer, the medium is the ether. What is this ether? The Lunists find conditions more and more uncomfortable the higher they ascend, for the density of the air, and therefore the amount of oxygen in a given volume of air, becomes less and less. Meteorologists have calculated that traces of the air we breathe may reach a height of some 200 miles, but what is beyond? Nothing but the ether, it is claimed. Light from the sun and stars reaches us via the ether. But what is this ether? We cannot handle it. We cannot see it. It fails to fall within the scope of any of our senses, for every attempt to show its presence has failed. It is spirit-like in the popular sense. It is Lodge's medium for the souls of the departed. Helmholtz and Kelvin tried to arrive at some properties of this hypothetical substance from a careful study of the manner in which waves were propagated through this ether. If, as the wave theory teaches us, the ether can be set in motion, then according to laws of mechanics, the ether 30 has mass. If so, it is smaller in amount than anything which can be detected with our most accurate balance. Further, this is a difficulty not easily explained. If this ether has any mass, why does it offer no detectable resistance to the velocity of the planets in it? Why is not the velocity of the planets reduced in time, just as the velocity of a rifle bullet decreases owing to the resistance of the air? Lodge, in arguing in favor of an ether, holds that its presence cannot be detected because it pervades all space and all matter. His favorite analogy is to point out the extreme unlikelihood of a deep-sea fish discovering the presence of the water with which it is surrounded on all sides, all of which tells us nothing about the ether, but does try to tell us why we cannot detect it. In short, answering the query at the head of this paragraph, we may say that we do not know. The waves are not all of the same length. Those that produce the sensation of sight are not the smallest waves known, yet their length is so small that it would take anywhere from 1 to 2 million of them to cover a yard. Curiously enough, our eye is not sensitive to wavelengths beyond either side of these limits, yet much smaller and much larger 31 waves are known. The smallest are the famous X-rays, which are scarcely 1/10,000th the size of light waves. Waves which have a powerful chemical action. Those which act on a photographic plate, for example, are longer than X-rays, yet smaller than light waves. Waves larger than light waves are those which produce the sensation of heat, and those used in wireless telegraphy. The latter may reach the enormous length of 5,000 yards. X-ray, actinic, or chemically active ray, light ray, heat ray, wireless ray, they differ in size, yet they all have this in common. They travel with the same speed, 186,000 miles per second. Powerful support to the conception that space is pervaded by ether was given when Maxwell discovered light to be an electromagnetic phenomenon. From purely theoretical considerations, this gifted English physicist was led to the view that waves could be set up as a result of electrical disturbances. He proved that such waves would travel with the same velocity as light waves. As there is not needed to transmit electrical phenomena, for you can pump all air out of a system and produce a vacuum, and electrical phenomena will continue. Maxwell was forced to the conclusion that the waves set up by electrical disturbances and transmitted with the same velocity as light were enabled to do so with the help of the same medium as light, namely the ether. It was now but a step for Maxwell to formulate the theory that light itself is nothing but an electrical phenomenon, the sensation of light being due to the passage of electric waves through the ether. This theory met with considerable opposition at first. Physicists had been brought up in a school which had taught that light and electricity were two entirely unrelated phenomena, and it was difficult for them to loosen the shackles that bound them to the older school. But two startling discoveries helped to fasten attention upon Maxwell's theory. One was an experimental confirmation of Maxwell's theoretical deduction. Hertz, a pupil of Helmholtz, showed how the discharge from a Leyden jar set up oscillations, which in turn gave rise to waves in the ether, comparable, insofar as velocity is concerned, to light waves, but differing from the latter in wavelength, the Hertzian waves being much longer. At a later date, these waves were further investigated by Marconi, with the result that wireless messages soon began to be flashed from one place to another. Just as there is a close connection between light and electricity, so there is between light and magnetism. The first to point out such a relationship was the illustrious Michael Faraday, but we owe to Zeeman the most extensive investigations in this field. If we throw some common salt into a flame and, with the help of a spectroscope, examine the spectrum produced, we are struck by the bright lines which stand out very prominently. These lines, yellow in color, are known as the D lines and serve to identify even minute traces of sodium. What is true of sodium is true of other elements. They all produce very characteristic spectra. Now Zeeman found that if the flame is placed between a powerful magnet and then some common salt thrown into the flame, the two yellow lines give place to 10 yellow lines. Such is one of the results of the effect of a magnetic field on light. The Zeeman effect led to several theories regarding its nature. The most successful of these was one proposed by Larmor and more fully treated by Lorentz. It has already been pointed out that the only difference between wireless and light waves is that the former are much longer and, we may now add, their vibrations are much slower. Light and wireless waves bear a relationship to one another comparable to the relationship borne by high and low-pitched sounds. To produce wireless waves, we allow charge of electricity to oscillate to and fro. These oscillations, or oscillating charges, are the cause of such waves. What charges give rise to light waves? Lorentz, from a study of the Zeeman effect, ascribed them to minute particles of matter smaller than the chemical atom, to which the name electron was given. The unit of electricity is the electron. Electrons in motion give rise to electricity, and electrons in vibration to light. The Zeeman effect gave Lorentz enough data to calculate the mass of such electrons. He then showed that these electrons in a magnetic field would be disturbed by precisely the amount to which Zeeman's observations pointed. In other words, the assumption of the electron fitted in most admirably with Zeeman's experiments on magnetism and light. In the meantime, a study of the discharge of electricity through gases and, later, the discovery of radium led, among other things, to a study of beta or cathode rays negatively charged particles of electricity. Through a series of strikingly original experiments, J. Thomson ascertained the mass of such particles or corpuscles, and then the very striking fact was brought out that Thomson's corpuscle weighed the same as Lorentz's electron. The electron was not merely the unit of electricity, but the smallest particle of matter. All matter is made up of some 80-odd elements. Oxygen, copper, lead are examples of such elements. Each element in turn consists of an innumerable number of atoms, of a size so small that 300 million of them could be placed alongside of one another without their total length exceeding 1 inch. John Dalton more than 100 years ago postulated a theory, now known as the atomic theory, to explain one of the fundamental laws in chemistry. This theory started out with an old Greek assumption that matter cannot be divided indefinitely, but that by continued subdivision, a point would be reached beyond which no further breaking up would be possible. The particles at this stage Dalton called atoms. Dalton's atomic hypothesis became one of the pillars upon which the whole superstructure of chemistry rested, and this because it explained a number of perplexing difficulties so much more satisfactorily than any other hypothesis. For nearly a century Dalton stood as firm as a rock, but early in the 90s, some epoch-making experiments on the discharge of electricity through gases were begun by a group of physicists, particularly Crookes, Rutherford, Leonard Röntgen, Becquerel, and, above all, J.J. Thomson, which pointed very clearly to the fact that the atoms are not the smallest particles of matter at all, that, in fact, they could be broken up into electrons of a diameter 1/100,000th that of an atom. It remained for the illustrious Madame Curie to confirm this beyond all doubt by her isolation of radium. Here, as Madame Curie showed, was an element whose atoms were actually breaking up under one's very eyes, so to speak. So far have we advanced since Dalton's day that Dalton's unit, the atom, is now pictured as a complex particle pattern after our solar system, with a nucleus of positive electricity in the center and particles of negative electricity or electrons surrounding the nucleus. All this leads to one inevitable conclusion. Matter is electrical in nature, but now if matter and light have the same origin, and matter is subject to gravitation, why not light also? So reasoned Einstein. Newton's studies of matter and motion led to his theory of gravitation and, incidentally, to his conception of time and space as definite entities, as we shall see. Einstein, in his theory of gravitation, based it upon discoveries belonging to the post-Newtonian period. One of these is Minkowski's theory of time and space as one, and inseparable. This theory we shall discuss at some length in the next chapter. Other important discoveries which led up to Einstein's work are the researches which culminated in the electron theory of matter. The origin of this theory may be traced to studies dealing with the nature of light. Here again Newton appears as a pioneer. Newton's corpuscular theory, however, proved wholly untenable when Foucault showed that the velocity of light in water is less than in air, which is the very reverse of what the corpuscular theory demands, but which does agree with Huygens' wave theory. But Huygens' wave theory postulated some medium in which the waves can act. To this medium the name ether was given. However, all attempts to show the presence of such an ether failed. Naturally enough, some began to doubt the existence of an ether altogether. Huygens' wave theory received a new lease of life with Maxwell's discovery that light is an electromagnetic phenomenon, that the waves set up by a source of light were comparable to waves set up by an electrical disturbance. Zeeman next showed that magnetism was also closely related to light. A study of Zeeman's experiments led Lorentz to the conclusion that electrical phenomena are due to the motion of charged particles called electrons, and that the vibrations of these electrons give rise to light. The conception of the electron as the very fundamental of matter was arrived at in an entirely different way from studies dealing with the discharge of electricity through gases and the breaking up of the atoms of radium. If matter and light have the same origin, and if matter is subject to gravitation, why not light also? And that's a wrap for today's show. We hope you enjoyed the ride. Thanks a million for being with us. Remember, the fun doesn't end here. We'll be back with another show soon. Until then, take care, stay awesome, and keep those smiles shining.